Hello, my name is Will Simonson, and today I'll be going over Lab 2, motion of a falling object in Physics 1. So the purpose of this experiment is to observe motion of an object that is dropped from rest and that falls to the ground without any outside horizontal force acting on it. We'll be using Newton's second law, the gravitational force, and the drag force to observe this projectile motion. We're going to compare the data that is observed through a tracker, which is observed data, and the data that is computed through GlowScript. So Newton's second law of physics, the momentum principle, describes that an object will move in a straight line at a constant speed when it experiences no net force. The net force is equal to the change in momentum over the change in time. No net force results in constant velocity, which is also no change in momentum. The force of gravity can be derived from the universal gravity formula, which is Fg equals the gravitational constant times the two masses over the position squared. So basically, if you set mass times gravity equal to the g m1 m2 over r squared, you can solve for little g, which will equal 9.97 or 9.8 once you cancel out a mass and also plug in the Earth's mass and position. So the larger the drag force, the larger the surface area, and that force will be opposite of vertical motion and will decrease the downward velocity. And the drag force is bv squared, and b is the coefficient based on size and the shape of the object. So materials that were used were a phone recording device, ruler, and a plastic pen holder. The system is the plastic pen holder. The surroundings is the room around the plastic and the ground. To do this, I set the phone on the table and press record. I dropped the plastic. I put the video in the tracker and used it to find a position versus time graph, and then I used GlowScript to evaluate the computational model with gravity, and then with gravity and the drag force using the initial position from the tracker. So then I compared the GlowScript and tracker models and analyzed the results. I found that the initial position was only in the y component and is 0.0183364, and the initial velocity was 0, and the final position was negative 2.497 meters. So falling down, so the y value is decreasing and the acceleration due to gravity is negative. Velocity versus time is a linear graph, while position versus time has decreasing velocity. There's acceleration due to gravitational force, which shows Newton's second law, F net equals Fg plus F drag. So this is the video that was used in the tracker, and you'll see here on the right side that it looks like the first graph is the y graph actually, and it should be going the negative slope of what is actually appearing here because the tracker put it in positive and I flipped the position values by multiplying them by -1, which ended up giving me a better slope. And so the code here, I used a change in time of 0.033, negative 9.8 for g. I used the unit vector of 1 in the y direction. So I found the time from the tracker and set t as less than or equal to 0.7. And basically for no drag, I used the momentum principle to calculate the loop added velocity to show the acceleration, which is caused by the gravitational force. And then with drag, I calculated drag using the formula I mentioned earlier and added that together with the force of gravity to find the total acceleration due to these forces and plug that in here. So this is the chart. You can see here that the lower is the graph that the tracker used. Oh no, the lower is the graph that was computed with no drag, and the top is with drag. And here you can see once I calculated with drag in the computational model, it became closer to the drag that it was experienced on observation. So what if the terminal velocity would be the same, even if it was thrown downward or initially from rest? Terminal velocity is equal to when the drag equals the force of gravity and a constant speed is reached. Initial velocity is not a factor. Only weight and drag coefficient plays a role. It should stay the same as long as an object does not change. The model that predicts terminal velocity is the model with drag force. The model with drag reaches a point with no acceleration. The force of drag is equal to the force of gravity, and they go in opposite directions.